So earlier we looked at a bomb calorimeter, and as it turns out, a bomb calorimeter measures the internal energy of a reaction because it doesn't allow work to happen by the reaction. But we can use constant pressure calorimetry to measure delta H of reaction. And in reality, most reactions in aqueous solutions are at constant pressure. In fact, most reactions in laboratories are at constant pressure because we do them and they're open to the atmospheres. So, the basics of the calorimetry method are the same. We assume conservation of energy, and we'll say something like, I have a chemical reaction and it's in a solution, and I want to measure the energy of the reaction. And so I'll be able to say Q of the reaction plus Q of the solution equals 0, and then I'll say Q of the reaction equals negative Q of the solution. Now, the Q of the solution is really whatever liquid is in here, and we can have a heat capacity for that and calculate that energy just based on the measurement of the amount of solution, the specific heat of the solution, and the temperature change for that solution. And then when we want to calculate the reaction enthalpy, that's really the number of kilojoules per mole of reactant. So what we usually end up doing is calculating the moles of the limiting reactant here. And then we calculate delta H for the reaction from that. The setup is the same one I believe I showed earlier. It's just a coffee cup. You have a glass stirrer, usually has a loop down at the bottom. And a thermometer that goes into it. You measure the temperature, and then you pour the two liquids together that contain the reactants. Usually put one reactant in one solution and one reactant in the other, and you mix them together, and then you observe what happens to the temperature after you mix them. So here's a typical setup. I'm starting with 50 milliliters of 3 molar sodium hydroxide in the container. I measure the temperature, so I have initial temperatures, and the second thing I'll do then is I'll add 50 milliliters of 3 molar HCl. So this is a heat of neutralization. I have HCl plus NaOH. These are both aqueous, and they'll form H2O liquid and NaCl, which is also aqueous, and that's the balanced chemical reaction, so 1-to-1 stoichiometry. So that's what will happen when I mix these two solutions together. And then in this particular experiment, the initial temperatures of both solutions were measured to be 25.74 initially, and when I mixed them together, the temperature rose to 47.10 degrees Celsius. So what is that actually telling me is going on, right? What it actually means is that when these two reactants come together, they go forward to form the products in an exothermic reaction, that is, they're releasing heat energy into their surroundings. That heat energy is picked up by the water, which predominantly makes up most of these solutions, and that water then temperature rises from 25.74 degrees to 47.10 degrees in response to the energy output of this reaction. So let's first calculate the energy for this reaction. We're going to do sort of this part here. We're going to calculate the energy of the reaction by assuming that the reaction is equal to the opposite of the energy of the solution, and then we calculate the solution energy. So I can write Q is equal to mc delta T. So M will be the mass of these two solutions together. Now, they're 50 mils and 50 mils, so volume of solution is going to be 100 milliliters. But to get the mass of the solution, I'll convert that over using the density. Now, the density isn't always 1, but in this particular instance, it's 1 gram per ml. And so this will end up being 100 grams. So this is, with 4 sig figs, the mass of my solution based on my density. Now, my specific heat, they tell you to use 4.18, and this is actually fairly realistic. Pure water at around room temperature would be very close to 4.184, but by adding some material to the solution, the heat capacity or specific heat of the solution changes just a little bit. So we can assume 4.184 or 4.18 joules per gram degree Celsius, and my change in temperature is T final minus T initial. So I can say its final temperature is 47.10 degrees Celsius and subtract my initial temperature, which is 25.74 degrees Celsius. And that will calculate to be 21.36 degrees Celsius change. Okay, so that's the increase in temperature from 25.74. It's 21.36 degrees Celsius increase. Now, I can plug all these variables in, all these values in to the variables in the equation, and I'll get 8,928.48 joules. I have three significant figures, so really that's my last significant figure, but I won't round yet. I want to finish my calculation first. Now what we need to do, going back to here, here. I need to calculate what my limiting reactant is. Oh yeah, here we go. Right, and then I'm going to divide my heat by the moles of reactant. Okay, so let's see. I have 50 milliliters of 3 molar HCl. So what does that come out to be, right? 50.0 mLs times 3.00 moles per liter. That comes out to be 150 millimoles. Now, when I do the same calculation for the sodium hydroxide, you'll notice the concentrations and molarities are the same. So either one of these could be the limiting reactant. So to calculate the energy for the reaction, I only divide by one of the limiting reactants since I have two of them. So I'm going to go ahead and say I'll just divide by this one that I calculated here. I need to know Q per mole to get my enthalpy of the reaction, or the heat of neutralization. So that's going to be the 8928.48 joules divided by, let me put this down below where I have a little bit more room. So I need to know the Q per mole. So that's going to be 8928.48 joules, 3 sig figs, divided by 150 millimoles. Now this needs to be in moles for this to be correct, so I'm going to show you a shortcut for the conversion, 150.0, and then you just substitute in the prefix for the milli, like that, 10 to the minus third, right? Remember, milli means 10 to the minus third moles. And then usually, although it doesn't say to do it in this problem, usually these are done in kilojoules. So we'll do 1,000 joules, or 10 to the third joules, per kilojoule. So when I run that calculation, I'll get 59.5. See, how many sig figs did I have? I had 3, right? So 59.52 kilojoules per mole. So that's going to be 59.5 kilojoules. Like that. Okay? So that's my energy per mole for that the water absorbed. But Q of the reaction, going back to here, right? Q of the reaction is negative the Q for the solution. So my thermochemical equation, I would write delta H is equal to negative 59.5 kJs. And this is for 1 mole of HCl or 1 mole of NaOH. So you could write per mole here, but oftentimes it's left off if it's written with the balanced chemical reaction.